Hi, everybody. Let's debrief the A-level problem, and more generally, how do you get better at problem solving? So, in other words, what can you do when you don't immediately recognize a solution approach? This is a major part of what mathematicians do. There's a handful of tricks you can use. It's not every trick applies to every problem, but in general, you have to make sense of the problem somehow. If it's a problem like the ones that we're working on, visualizing the problem by making a labeled diagram makes them easier to think about. In general, like being clear about what information do you know, and then what information do you want to know, and then other things that you might be able to find that could be related, and then think about what math you already know that either connects to what you want or connects to what you're trying to find. And you're not going to jump straight to the solution. You're going to kind of work your way in steps. You're going to say, oh, maybe I could try this thing. That'll let me figure this out. What can I do from there? So it's going to feel more tentative, and you have to feel comfortable with that because there is no shortcut. That's just the way problem solving works. Here's like a super simple example. So let's say I have a bunch of stacked right triangles. I know this is length 2, all of these things are length 1, I want to know how long this is. So this would be a difficult problem to someone who is very new at this. But what you can say, because like I don't know how to jump straight to the answer, but you say, okay, look, I know Pythagorean theorem connects to right triangles, and I see that I can apply that here. So I would know how to figure out that hypotenuse. Once I know that hypotenuse, I see that now that hypotenuse is actually the bottom leg of this triangle, so I could use the Pythagorean theorem again to connect this and this to find that one. Oh, I see, and now it's just a chain, and that's eventually going to lead me to my solution. So that's a very simple illustration of the idea that you're not going to jump to the answer, but you're going to think about what else could you figure out in a chain that leads you to the answer. Okay, so here was the A-level example. I removed the diagram because the diagram is actually a thing that you should do. I put it in there to help you. So if I have this vector path that describes my movement, and my friend has a different vector path that describes their movement, like what are the coordinates where my path is going to cross their path? And then figure out how to adjust my speed so that I'll bump into my friend. In other words, so we'll be at the same location at the same time. Okay, well, I mean, these equations don't immediately mean anything to me. Like, I look at them and I think, equations. So for me, I think very visually. So if I say, okay, look, my friend starts here at 10,3. Oh, I see they're walking straight to the left. Like with a picture, now it's much easier for me to kind of picture the situation. I start here at -5 and -2. I'm walking in the direction of 1, 4. Not the location 1, 4, but I'm walking over 1, up 4, but scaled down a little bit. And so that's sort of approximately headed in this direction. So now I can actually imagine, my friend's sort of walking along this way. I'm walking along this way. I can see that the paths are going to cross kind of somewhere here-ish maybe. And so now I can start asking, what do I know? What do I want to know? Like, what connects? What else could I find? So there was a couple ideas that came out in class. Some people thought, okay, let's actually imagine the lines that represent the paths. So here we've just got a horizontal line at y = 3. Here we'd have a line. And some people thought, okay, wait, if I want to know where do two lines cross, we know math that does that, back from Algebra 1, intersection of two lines. The problem is a lot of groups got stuck there because they thought, okay, but I don't see how intersection of two lines can kind of connect to what we have. So this is the next thought that a mathematician would have, and it's a very easy thought to have. You just have to realize you need to do it. So you're thinking, okay, look, in Algebra 1, we knew how to find the intersection of two lines. So what do we need to apply the math we know, and what do we actually have? So if we were going to apply the Algebra 1 techniques, the Algebra 1 technique you used for things like this. If I have two lines, how do I know where they cross? Like the problem would need to look like this. What does our problem look like? So in our problem, we don't have Cartesian paths for lines, we have these vector equations. So then you need to think, okay, is there a way of turning what I have into what I need so I can use the math I know? This is the key moment of connecting. This is what most students find the most difficult. And one of the reasons it's difficult is because you have to have in your mind what are all of the things that you know how to do, and then decide which of those might apply. So if you think back, we actually did a lot of work where when you were first learning about the lines, you know how to rewrite this as the line that it represents. Like we know that this tells us what the slope is, this could tell us a point on the line, and if we know a point on the line and we know the slope, you can write the equation for the line. So just like in this problem where we weren't sure, but then we started chaining some things together. We said, oh, we could figure out this, which lets us figure out this, which lets us figure out this, which gives us the answer. Now we've got the same idea. We say, we need to figure out the intersection point. If I knew what the lines were, I could do that. What we have is this. Oh, but I know how to take this kind of equation and turn it into Cartesian equations, and then that'll let me find the intersection point, and then I'm done. So see how it's the same idea of chaining together. But here what you're chaining together is the same technique applied over and over again. Here what you have to chain together is more abstract ideas about what you have, and then what you want to have, and then math that connects them. So this came from the whiteboard of a student in, I think, second block. So here they said, okay, this equation, it doesn't matter where they start. Well, it does matter where they start, but once they've started, we're only walking to the left. So we're starting at a y-coordinate of 3 and walking to the left. So that's just the equation y equals 3. And then this one, they're thinking, let's use point-slope form. We'll start at this point, and we'll use the slope, and then you can solve for the intersection point. Some other people thought, let's just set these two equations, the equation for m and the equation f, equal to each other. Some of them did that without actually thinking about why is that a good thing to do? Like, is that going to help us? It's not a problem to ask what would happen if. That's a great math question to ask. But you have to be able to think hard enough about it to know the answer to that question. So if I was going to set these equal to each other, what could I do from here? I mean, most people are thinking, I'm going to solve. But if you're solving, what are you solving for? I think there's only one answer. I would be solving for t, because that's the only variable. What would it mean if we solved for t? It must mean that we're solving for the time when this vector is equal to that vector, when this vector is pointing to the same location as that vector, because we're treating our vectors right now as position vectors. Is that connected to what we want? For sure it is, because we want the time when the vector that points to this guy's position is the same as the vector that points to that guy's position. Because if they're the same, that means they're at the same position. But wait, now I'm stopping to think about it even harder, and I'm realizing, is there actually a time when they're going to be at the same place? That's part B of the problem. I need to adjust my speed so that that's going to happen. So maybe it actually doesn't make sense yet to set these equations equal to each other, because yeah, like this guy's, well, let's see. What I'm trying to do is I'm trying to imagine who's going to reach this position first, like the intersection point. So this guy's going fairly slowly because it's this 1, 4 vector, but it's been scaled down by 7. And this dude's walking at like 1 unit left per second. So after like 13, like 12 to 13 seconds, this guy's going to be over here. Well, I don't know. It's a little bit hard to estimate. But yeah, because of part B, we know that actually this isn't going to work yet. There's not going to be a time when they're both at the same spot. But it does give me a different idea. I could ask, when is this guy going to have a y-coordinate of 3? Because if I ignore this dude, if I just want to figure out where they're intersecting, I could say, all right, when does this guy actually hit y equals 3? And then once I know the time, I could plug that back in to figure out this guy's x coordinate, and then I'd know where do the two paths intersect. So I want to illustrate, I had to grope my way into that realization. It didn't pop into my mind. I had to mull it over. I had to think, okay, could I do this? Would that make sense? Oh, it doesn't quite make sense. But wait, it makes me think, as this guy is walking, if I could figure out something, then I could figure out the thing I wanted. So that's the type of thinking you need to do. This is the what else could I find? So if I could find the time when the y coordinate is something, that connects, because then I could find the x coordinate. Well, how would I do that? So remember that you can split a vector equation apart. We did this once when we said they're the same as parametrics. So you could think, all right, I don't care about the whole vector equation. I just care about the y component because I just want to know when is y equal to 3. So I could just take the y parts. At a particular time, like t equals 10, the way I'd figure out the y coordinate would be I start at -2, I'd plug in 10 for t, I'd divide by 7, and then I'd multiply by 4. So I can write that down as its own equation just for the y coordinate, and then I'd have something I can solve, because I can plug in 3 for y, solve for t. Once I know t, I can plug that back into the original to find x. So, it might feel a little bit daunting. I know it feels uncomfortable not to have a process that that you can follow that leads to the answer. But this is what it means to grow as a problem solver. If there were a process, we could just have a computer do it faster than you can and more accurately than you can. So, this is developing your mind. This is literally making you smarter. And it's a thing you can practice, and it's a thing you can get better at. So I'm going to kick out some more practice problems. I'm not going to make them too different to start with, but realize that when it happens on the test, I'm going to try and make it look very different, because otherwise I'm just testing, can you follow a process? And I don't want to test that. I want to test, can you do this stuff? Can you notice stuff? Can you decide what math might connect? Can you decide what you might need in order to make it connect? Okay, good luck.